of all, I'd like to warmly welcome you all aboard on this Dekati webinar. Today's topic will be Brakeware particulate matter emission measurements in wide particle size range. And a couple of technical things first related to this Zoom webinar platform. Feel free to add questions in the Q&A section anytime when you come up with some questions. And then there is also the chat tool, which you can use to comment and share your experiences, for example, or however you like it. So feel free to use the Q&A and the chat functions. I have a couple of points where I have some time to look at the questions, and my colleague Erkki also will then interrupt me in case there are questions. So also at some other points of the webinar. But without further delay, I will start the webinar presentation now, and I will actually stop the video so the bandwidth will be purely in the purely used for the presentation itself. So here are the contents of today's Dekati webinar. First of all, we will have a brief look at the Dekati, the company and the products we manufacture and develop. Then we will go into the today's agenda of Brakeware Emissions, look at the relevance and also brief look at the characteristics of the Brakeware particle emissions, then the sampling, how it's usually done, just the basics in terms of brake dyno and sampling. Then we'll have a look at the actual measurement possibilities, how to do it in wide size range, and also the post-analysis capabilities. And then at the end, we will have a few case examples to have a look at how these studies have been conducted. Just a few examples of those. A couple of words about Dekati. Dekati has been around for over 25 years now, and we sell, manufacture, and develop new fine particle measurement solutions. And the core competencies is in real-time measurement instruments for wide size range, and also sample conditioning for all kinds of atmospheres and all kinds of measurement applications. Dekati is a privately owned company, originally from Tampere University of Technology Aerosol Physics Lab. So spinned off from there, and we're located in Kangasala, Finland, and most of our sales go to export, and we have a wide distributor network. We have over 20 high know-how employees in the company, and very recently we got the ISO accreditation also. And we'll not go through this in detail, but we have a product, we have several real-time instruments. Then we have impactors for gravimetric measurements, like offline methods. And then we have a variety of sample conditioning devices to also get the sample from high temperature and high concentrations. And our instruments are being used in a variety of different applications. Today, we will focus on the automotive application, and to be more precise, on the non-exhaust one of the non-exhaust applications. But the Dekati instruments are widely used in, for example, air quality, combustion studies, nuclear safety, and also, for example, filtration research, which was the topic of the previous Dekati webinar, which you can find on our YouTube channel if you want to have a look at that as well. Okay, let's hop into Brakeware emissions then. So when we look at traffic and road transport, there's a way to categorize the particle emissions coming from the traffic into non-exhaust and exhaust emissions. And actually, according to the studies, their contribution to total ambient PM10 emissions are roughly equal nowadays. And the exhaust emissions are obviously related to the combustion in the gasoline or diesel engines most often. And most of these exhaust emissions then come out of the tailpipe of the vehicles. But then if we look at the non-exhaust particle emissions, their sources, their most significant ones are brake wear, tire wear, and road abrasion. And according to the studies, brake wear contributes to about 16 to 55% of non-exhaust emission PM. And the largest fraction is seen in the urban areas because of the braking frequency is higher, and obviously also a lot of vehicles there and a lot of stops. And the Brakeware emissions aren't yet regulated. There is work being done towards the legislation to work on recommendations for that, but that is still yet to come and under processing. And today we will focus on the brake wear, although also tire wear, for example, is being studied and researched more and more nowadays. And if we look at the development of the situation with these non-exhaust emissions, this is from UK Department for Transport, and they looking at their graph, we can see that the decline in this century in exhaust emissions for PM2.5, so particulate matter under 2.5 microns, the decline has been very fast. So we are already in a situation where the non-exhaust PM2.5 exceeds the exhaust PM2.5 because of the more efficient cleaning and filtration and the engine technologies and the after treatment. And this is mostly for diesel and DPF filters, for example. But if we look at what they forecast to be the situation, for example, in 2030, the non-exhaust PM2.5 will already be about 10 times the amount that the particle emissions PM2.5 come from the tailpipe. So this is one of the reasons that the importance of the non-exhaust particle emissions is rising and has been rising for some time now. Here is another graph from the same document and this shows the PM2.5 and PM10 emission inventories submitted by Germany as an example. So again, the exhaust has gone down quite a bit, but the tire and brake wear emissions and road abrasion has gone up, in fact. So then we will have a brief look at how these breakware particles are actually, where do they come from exactly? So here we show the most, probably the most usual suspect in breakware particle formation, the disc brake system. So there's the brake pad and the brake disc, and when the brake pad is being pressed against the brake disc that is on the brake caliper, that causes the friction that then decelerates and eventually stops the vehicle. And this physical contact causes friction, and this friction causes obviously mechanical wear to these parts when they are pressed together, and the disc is in fast motion. So this is then causing larger particles, and the coarse mode is caused by the friction. And then on the other hand, the brake disc and the pad, they get into quite elevated temperatures because of this friction. And when they are hot enough, there happens some volatilization. So some of the material evaporates, and that then causes the nucleation and accumulation modes. So the much smaller particles down to nanoparticle sizes. So all in all, the breakware particle emissions come in wide size range. And another important aspect of the breakware particle emissions is that the spectrum of materials is very wide as well. So this concerns especially the brake pads. So they actually, there actually is a way to categorize these materials to non-metallic, semi-metallic, fully metallic, and ceramic. And under all these categories, there are a huge variety of different materials that are being used to optimize the performance of the brake pad. The brake discs are usually cast iron, or then, for example, in racing vehicles, ceramic materials. And here we can see an example of the just the different modes of particle emissions or particles in general. So there's the nucleation mode that is around at around 10 nanometers, can be there, for example, and these primary particles then, when they coagulate and agglomerate, they cause also the accumulation mode, and also condensation plays a role in this size of the particles. And then the mechanical processes in this case usually cause the coarse mode, which is then around several microns in size range and can be also over 10 microns. So in breakware particles, we see all of these three modes, obviously depending on the type of braking and also the materials and the speed and the temperature. But in general, the size range is wide. Because of the relative contribution of the breakware emissions to the total emissions and ambient PM, there is actions going on to try to reduce these breakware emissions. One way to reduce the breakware emissions is the braking systems in electric and hybrid vehicles, which is something that obviously the reason behind electric and hybrid vehicles isn't to reduce breakware emissions, but they happen to reduce them because in those vehicles the regenerative braking does not involve the pad disc contact. So actually the engine is doing the braking. Obviously they have the disc brake systems in place, but the need to use them is less, also depending on how the driver uses the brake and how soft is he or she braking. Then there are ways to reduce the particle formation by actually doing new formulations for the materials, and things like heat treatment of the brake disc. So that is also one thing that is very, very important, and is something that does not require to build a new vehicle, but just build parts of it and make them better. Then one way to approach it is to actually add filtration. There are some challenges in this because obviously if we look at the exhaust pipe, for example, it is quite convenient to introduce a cleaning system into a tailpipe, but if you look at the brake disc and pad, there is no such a straightforward way to clean the emissions, so it has to be basically around the whole brake system. But some studies estimate that with this it could be possible to reduce about 30 to 70% in particle mass. But new innovations for this are still being developed. And a motivator in more and more in the future for this will be that most likely the Brakeware Emissions will have regulations and limits for the emissions in the future. We don't yet know what the limits will be, but in any case they will then also probably accelerate these actions a lot more.
Sorry, Oskari, we actually have a question in Q&A.
Okay, let's see. Okay, and we have a question here. Do you think the accumulation mode particles are only caused by coagulation of nucleation mode particles? In our measurements, we see particles of the same size already when the brake is still cold, and thus without nucleation generated particles. Good question. Thank you for that. Actually, this I agree that the accumulation mode does not come purely from the coagulation. So I agree that also in the results that I have seen and in the measurements I have been involved in, that the accumulation mode does not only come via these small primary particles. So there are also emitted straight from the process itself. So thank you. I agree on that, and probably was something that I did not cover clearly when talking about this particle formation. Thank you. Okay, then if we look at the sampling, here is an image that I drew, which is a simplistic way to show the basics of the particle measurements done from a breakdown. So usually the interest is to simulate the actual braking event. So you need to have a brake disc and a brake pad, and in order to have a look at the emissions, and actually only the emissions coming from the braking event, usually some enclosure is needed. So the basic idea usually is that we need to have a controlled amount of air flowing into this enclosure, and then we have to make sure that there are no particles in in the air before the break event happens. So we feed air, and the air is being cleaned in the HEPA filter. Then particle-free air is entering this break chamber, and then the break itself is usually operated according to some defined drive cycle, for example, WLTP. And after the airflow has gone through the break chamber, obviously then it will carry the particles emitted by the breaking event. And then the airflow is usually led into a pipe, for example, where it has some time and distance to mix up and to be evenly distributed before it enters the sampling nozzle. And usually it is recommended in this application to use isokinetic nozzles if we're measuring and also studying the larger particles. So the isokinetic nozzle, which size is defined by the speed of this flow going in this pipe, then make sure that the amount of the larger particles, let's say roughly larger than 1 micron, are not being under or overestimated when the flow is being drawn into the particle measurement instruments. And usually then this flow is created by a vacuum pump that then sucks the sample into the measurement instrument to be analyzed. And then the excess airflow is being let out. Okay, let's have a look if there are questions. And actually, we have one new question here. Has the disk ancing have an impact on the emitted particle number? Most definitely, it has an impact in most materials and cases, and there are also studies showing that the amount of particles emitted from a fresh disk can be very different from the emitted or the emissions after the disk has been used for some time. So definitely it has an impact. For isokinetic condition, why only 1 micron meter size are overestimated or underestimated? Well, unfortunately, I think we won't have time to go into this in very detail in this presentation, but the basic idea is that if the flow, because there is flow and suction inside this nozzle, which is caused by the vacuum pump that sucks the sample into the particle measurement instrument. If it's too high, the flow taking the sample in, then it will not only take the large particles or the particles that are going in the stream into the nozzle, but then it will also pull some of the particles from the side and not take a representative sample. And actually, in this case, it then underestimates the amount of large particles, because the high suction actually then affects more the smaller sized particles that are being taken from further away, because they are smaller, they are more affected by the high suction here compared to the larger chunks and particles that are going in the streamline a bit further away. The suction is not enough to also pull the same share of those into the nozzle. And on the other hand, if the nozzle does have a too low flow at the tip of the nozzle, then it will overestimate the larger particles, because the larger particles will will go according to the streamlines, but then again, it affects more the smaller ones, that they are drawn to the sides then more easily, because the flow around the nozzle is higher, so it's pulling the particles away. So it has to match the flow around the nozzle to make the sample representative. I hope this answers at least a little bit. It wasn't that precise explanation, but that is the basic idea for isokinetic sampling. Okay, thank you for the questions again.
There's still one more.
Okay, let's see. Here we go. How do you recommend to set up the sampling in the case you have more than one particle measurement system? Well, it depends, but one option is to split the flow after the nozzle for several systems, to have more pumps here, for example, and more particle measurement instruments. Then we just have to take into account that the flow here in this tube will be the sum of all these flows going into the instruments, and the nozzle size has to be chosen accordingly. Another option is to add more isokinetic nozzles each, and then calculate them according to the specific instruments and their inlet flows. But in many cases, it might be convenient to use one nozzle for several instruments, but it depends on the specifications, obviously, of the instruments as well. But the good side of having one nozzle and one sampling line, then spread to and distributed to 2 or 3 instruments, for example, is that then the sampling line is more, or more of the sampling line and the nozzle is same for each instrument, so it's more comparable, and one less factor behind the differences for the possible differences shown by the instrument and their results. Thank you. Right. So now we will have a look at the measurement solutions, or some of the measurement solutions we have provided for this application. So let's have a look at the Dekati ELPI Plus, so the electrical low pressure impactor. So the features of this instrument is that with it you can get a real-time particle size distribution and concentration, and it gives the results in 1 Hertz or up to 10 Hertz. So it can cope with transient drive cycles, for example, and keep up with the pace, and show also the quick changes in the size distribution or concentration readings. From the instrument response, the number, mass, volume, surface area, or LDSA can be calculated. I will show the operating principle in the next couple of slides after this. Also, it enables to measure the particle charge, net charge size distribution. So you can also have measure the natural charge carried by different size particles. Their net charge and size range is wide. It goes down to nano sizes down to 6 nanometers and up to 10 microns in size. So it fits well, for example, when you want to look at the PM10 or PM2.5 size area, and it's very precise, and resolution is at its best in the lower sizes. there are 14 physical size fractions, 14 stages in the Impactor, and with the high resolution software, it is possible to have a look at the results in 100 or 500 size fractions. And the high resolution software is not just a fitting done to these 14 stages. It uses the collection efficiencies of each stage to put together actual high resolution size distribution. The picture here on the right hand side is some Brakeware data measured with the high resolution LP+. Not only the size range is wide, but also the dynamic concentration range as well. So it can be used from ambient air measurements to also much higher concentrations. When using the analysis plates, all the particles are collected, and therefore it's possible to do post-analysis for them. And with the sintered metal collection plates, in cases that there is no need to do post-analysis, then these sintered collection plates can hold a much larger quantity of particulate matter on them, so they enable very long-term measurements. So up to 6 months, you can run it up to 6 months, 24/7 in ambient air, for example. This is what we did in Tampere area in Finland, and the instrument after these measurements and without any cleaning in between still passed our tests against the reference instrument. All right. So the operating principle here is a simplified image, and a look at that to save that some time. So the basic idea is to charge the particles first. So at the inlet, after the inlet, there is a charger that gives positive charge to the particles. It's a diffusion charger. And after the particles have been charged, they enter the cascade impactor, which then size classifies the particles according to their aerodynamic size. After the cascade, or with the cascade impactor, into each stage there is connected an electrometer, and all the stages are insulated from one another, and the electrometers detect the total particle carried charge on each stage. So because we know the charger efficiency, and we know how much charge certain sized particle gets, then when we measure the charge with these fine electrometers from each stage, we get the real-time size distribution that way. So here's an image just showing all other things connected into this basic idea. So we have the charger and pre-separator that separates the over 10 micron particles in the beginning, and there's a tungsten needle and a high voltage source to cause a flux of positive ions to charge all the particles, and then they enter the impactor. And there are electrometer needles then connected to the each stage of the impactor. And the last stage is a filter stage which collects all the particles smaller than approximately 15 nanometers, and then gives also the electrical reading and the real-time reading from that. But for all the other sizes, you also get the particle collection. And flow control is easy because the smallest holes in the stages at the lowest stages act as a critical orifice. So when the low pressure is being set to 40 millibars, then the flow is always the approximately 10 liters per minute. The precise value is then the calibration sheet of each instrument, but doesn't need any flow controller. That should be calibrated from time to time, for example. And it can be used as standalone, or it can be connected to a PC with, for example, RS-232 connector to USB or Ethernet connector, for example. There are different options. And one important aspect in many Brakeware emission research cases is the possibility to do post-analysis. One of the reasons behind this is, again, the very complex nature of the materials and mixtures in the brake pads, for example. So the LP Plus collects the size classified particles on 14 different collection plates. Usually aluminum or polycarbonate collection substrates are being used, but other thin materials can be used too if necessary. And when the sample is connected onto these collection substrates, after that it enables various kinds of post-analysis methods. For example, basic weighing to get the actual gravimetric mass, or microscopy images, elemental analysis, and all kinds of chemical analysis, depending on the objectives of the research. And I mentioned here also the DLPI, which is the Dekati low pressure impactor. So we also have in our product line impactors that don't give out any real-time data. So there's no charger or electrometers connected, just the impactor itself. So with those, you can get the gravimetric mass and all the other post-analysis possibilities, obviously too. If the objective is only to look at the post-analysis of the size classified samples. Then another instrument I will show you briefly of our product line is the Dekati E-filter. So the E-filter is a combination of a traditional standardized gravimetric PM filter holder combined with a real-time detection module. So this enables the studying of the mass of the sample. You can look at the total mass emitted, or if you have a pre-cut, for example, a cyclone in front of it, PM 2.5 is also possible. But if you only have a gravimetric filter holder, you don't get any real-time data. Obviously, you only get the one reading of PM once you've done the whole process of weighing the filter and conditioning it first, and so on. So with this instrument, you also get the real-time signal that gives insight on when most of the sample was collected, and also you can then compare different measurements with one another and do kind of quality control as well. And the real-time signal is related to the surface area of the particles, and conversion to other metrics is also possible. Real-time measurement then provides obviously some extra information that wouldn't be possible with only the filter holder. And the basic idea is that there is the PM filter holder designed according to standards, but there's a small side flow of 0.5 liters per minute pulled with an internal pump into this detector block. And the detector block has a charger and a single electrometer connected to a Faraday cup filter inside it that gives the reading. And it can be used battery powered, or the power cord can be also connected all the time. And here is the operating principle image. So some similarities to LP+. Again, there's the corona discharge. The charge is the particles. Ion trap to remove the excess ions, which is also there in the LP+, which was not mentioned, but then the Faraday cup filter then is there to collect the particles, and the electrometer is connected to this filter to measure the current carried by the particles. And a small pump to pull this ½ liter per minute flow is inside the unit, but then for the actual gravimetric filter collection, a separate pump with flow controller is needed. I see there are a couple of questions. I could have a look at this point. One question is, which substrate do you recommend for SEM examinations? Well, this is a good question. I personally don't have experience on doing the electron microscopy, but I would personally look into some previous research and have a look at that. Also, I'm happy to have a look at this myself and with our team. So if you want to approach us, for example, sales@dekati.fi will work well, and we can have a look into this afterwards. Thank you for the question. And also if there are some people with experience, they can also type into the chat if they have used some specific material. Another question here: is it possible to determine an effective particle density for the 14 impactor size classes with the LP+ by comparing the gravimetric mass and the calculated particle volume? If it's possible, which minimum collected particle mass is necessary for such a procedure? Yeah, it is possible to use the gravimetric mass. Yeah.
May I comment?
Yeah.
Maybe
yes,
quickly.
please.
Yeah, this is would be maybe another seminar. We have a technical note about the effect of density on the LP+ result, and the effective density has a bigger effect on particle number size distribution than the mass size distribution. So the mass size distribution is actually not a lot affected by particle density, because it affects the size and the concentration calculation in different directions. So usually if you look at the way that the LP or LP+ has been used for density studies, it has been used by combining it, for example, with an SMPS and comparing those number size distributions from the two instruments. So it's usually done by the number size distribution and not via the mass distribution, because the mass result of the LP+ is actually not a lot affected by particle density, but we have quite a detailed technical note on this. If with that we can send out if you have interest in this. There's also a couple of questions in the chat.
Okay, yeah, there is a mention that 10 Hz was not recommended to us as less accurate. This is a good comment. Indeed, especially with and this question concerns the LP+ now. So if the concentrations are quite low, the 10 Hz naturally causes a little bit more noise into the noise signal ratio, and usually also when looking at transient drive cycles, the 1 Hertz, so 1 data row, 1 size distribution per second is definitely enough for the speed of the measurements and the quantity of the results per time. So yes, I imagine that, and I also have encountered that in most cases in Brakeware measurements, the 1 Hertz is a better choice. And another question was, how can LP Plus be connected to Ethernet? This is actually instructed in the LP Plus user manual, and also we can guide you further via email if you like. So, but the basic idea is that there's an Ethernet cable connector on the back side of the unit, and it can be then connected into a network and then connected via IP address into that, or straight. Or it's also possible to use the Ethernet cable for a straight up connection to a PC. All right, thanks. Well, we covered the questions now. For now, let's go into the few case examples. I chose these examples just on the basis that to demonstrate the different possibilities to do with the LP Plus and Brakeware particles. So here's couple of images from a presentation shown in a conference in SAE Brake Colloquium by Alemani and others. So this was pin on disk study. So in this case, there was no brake chamber similar to shown in the previous picture, but it is another traditional way to have a look at the emissions and their characteristics, is to have a pin on a brake disc and look what comes out after that. So, but again, the basic idea in the setup here is to insert clean air, and then it goes through this chamber and it is then being sampled. So here was LP Plus sampling and also FMPS and OPS. And what they were able to do with the LP Plus is to collect the images also for, or collect the samples also for post-analysis. And here are some electron microscopy images taken from different size ranges from the collection substrates of the LP Plus. So just as an example of this post-analysis. Moving on, so we will make it through the presentation. A couple of images from the same presentation. So they were also able to do this energy dispersive X-ray spectroscopy to have a look at the different materials found in the different brakes that were studied in the test, using the sample collected on the LP Plus collection substrates. Here are a couple of slides about particle emission measurements we did together with ITT and Air Modus in Italy. So these were presented in a PMP meeting in 2019 by Mikko Moisio, and they have quite a similar setup to what I showed in the simplistic image. They have a inlet HEPA filtered air going in to the brake chamber, and the measurement and sampling point after the chamber. And in these measurements, we had LP Plus, then we had the E filter and Air Modus CPC, and we also had a pre-cut cyclone PM10 cyclone, which are also available from Dekati. And this case, well, LP Plus has a pre-cut inside it, but this was mostly here to protect the CPC from malfunctioning from the larger particles. But also, as mentioned, the cyclone collects all the over 10 micron particles into the cup, so also enables post-analysis of those. Here are a couple of separate WLTP cycles. Duration of a WLTP cycle is about 6 hours. So to demonstrate the Dekati E-filter real-time data in actual Brakeware emission measurements. So we found out that the repeatability looked really nice. We did several of these WLTP cycles after one another without any actions in between. Here is then a comparison of LP plus number concentration, CPC number concentration. Those are there in blue and orange. The yellow one is the E-filter real-time reading. The black step functions at the bottom are break events, and the break temperature is shown with the red line here. So we can clearly see the not only the temperature but also the particle number concentrations peaking after these break events, and some of the events are then harder than others. At the middle, we can see a significantly harder break event. And here is a similar picture with the size distributions then. So just to demonstrate that then it is possible to, using the data, not only look at the concentration readings, but also to then have a look at what does the size distribution look like in different kind of phases in the drive cycle, and for example, also looking at the peaks. And again, showing that also the size distribution in this kind of peak can have a definitely also very high concentrations, looking at number size distribution too in also some of the higher sizes, not only the nanoparticles. And this example is then a bit different type of study done by Pericone and others. It was concerning the volatility of Brakeware emissions. It was done by Brembo, Technical University of Ostrava, and KTH from Sweden. Here the idea is that the volatility of emissions is often important because, for example, in urban background, only for example, 1/3 of the PM2.5 can be attributed to primary aerosols. So a very large part of the actual PM2.5 concentration in the air that we breathe can originate from secondary aerosols that are formed, and they wanted to then study this effect or this phenomenon in Brakeware emissions. And they pointed out that break events are a transient and a high sampling frequency instrument, and high size resolution is necessary for these kind of studies, and the opportunity to use with heated sample and in combination with different sampling solutions and sample conditioning solutions was vital. So what they used in setup is that after the break chamber, they sampled with LP plus in 3 different settings. So they had one LP plus with just a standard sampling line. Then they had the high temperature LP plus version with the heated sampling line. So the high temperature LP plus is a version where also the impactor part is heated, can be heated up to 180 degrees Celsius. So you can measure a hot sample without the need to dilute it in any way. And then the third setup was a thermodenuder with LP plus. So they then compared the results with the different setups. And just as an example, you can have a look at the study. It's open access. So we unfortunately don't have the time to look at it in detail, but just as an example, here is one graph that shows that the high temperature LP plus, for example, in the beginning half of this drive cycle showed much lower readings than the standard because there was volatile species also involved in the particle matter that was emitted. So they found out that there were considerable differences depending on whether they eliminated the volatile species or not. And to conclude, I will have a look at the last questions after this. So the particle size range is wide, and there's definitely a broad mixture of components and materials. And usually the measurements are done over a transient drive cycle that are already predefined. And for these studies and research purposes, the LP plus and moreover the high resolution LP plus, if more channels are needed, for example, to look at the number size distribution, is definitely a useful research instrument for this application, because with single instrument you can cover the whole size range. You don't have to have several different instruments with different working principles, and also you get the size distribution actually second by second. For example, you don't need to wait for it to scan, for example, to have the size distribution over this size range, which is vital in the transient conditions. And not only you get the real-time data, but also with exactly the same sample, you can do the post-analysis afterwards if that is of interest. And also a good thing is that in this application and with the LP plus concentration range, usually there is no need for any dilution systems. And eFilter is then another possibly interesting instrument with the measurements where the size distribution is not the point of interest, or it's more the collection of the particle matter on a single filter, and possibly the post analysis on that, but also getting data on the real-time concentration. Okay. Thank you, and I will have a look at the questions now to wrap it up. One question is, how frequently do you need to clean and maintain the LP plus, and how can counting efficiency change over time? Thank you. In general, again, this depends a lot on the concentrations, but now as we are focusing on the Brakeware emissions, according to my experiences, it is possible to do like, even with the analysis plates where you have the smooth collection substrates, you can, for example, have it running a day or two with drive cycles going going on and not needing to do any maintenance in between. In between depends on how rough the cycles are, obviously, and how much particles are emitted, but it doesn't need to be cleaned and maintained all the time. And it is actually quite long, and it is 5 to 10 times longer if you use the sintered collection plates, roughly. So it is not easy to put a certain number, but the loading in the Brakeware application usually doesn't overcome or doesn't appear too quickly, so that it would be a pain to keep cleaning it all the time. So not usually an issue in this application. The 14 LP stages are Faraday cages, which means that a negative response should be measured for all particles passing into it, even if they are not impacted, and those leaving it will give a positive response. How is this corrected for? Well, this, I would say, this also would require quite a bit of time to go through this in detail. Actually, we had an LP Plus webinar last autumn. We probably could have at some point a webinar where we go into the details of the operating principle, also looking at this, but yeah, maybe if you, Erkki, want to briefly sum it up, you might.
Yeah, so maybe going as briefly as possible. Yeah. That's exactly what happens when the LP is doing the measurement. So it's a difference between the current going in and current exiting a stage. However, usually this happens in a fraction of a second, because all in all, the sample only takes less than 1 second to go through the entire impactor. So it's only a fraction of a second per stage, and that is really what we are measuring all the time, is the difference between what is the current going in and what is the current going out. And so that is where we get our signal. So that's why it doesn't matter if you're using an insulative collection substrate or if the particles themselves are from electrically insulated material, because we are not measuring the current from the particles themselves. We are measuring the difference of the charges entering the Faraday cage and the charges leaving the Faraday cage.
Yes, thanks. How to measure larger particles than 10 microns? Well, if you want to have real-time signal for particles over 10 microns, then I'd say the optical instruments are a tool for those very large sized particles. Then with the Dekati instruments, post-analysis for over 10 micron particles and collection of them is possible, though. So depending on what is the measurement and what is the metric needed for those largest particles. How long is the scanning time? The LP Plus does not do a scan, so it operates so that it instantly it keeps getting the electrometer signals even up to in 10 hertz. So basically it's once per second or 10 times per second. So it really gives you a second by second data if it's in 1 hertz of the size distribution, because it gives the readings simultaneously for all the size ranges or all the stages of the impactor. And there's still a question, is the instrument stable under vibrations? Well, the LP Plus has been used also in onboard measurements. So with a proper installation, it is possible to stabilize it also under vibration so that it works well. It requires some planning on how to, if let's say if you would put the LP Plus located on top of the vacuum pump, for example, then it obviously is very much vibrating all the time. So that kind of vibration has to be taken care of with some padding or something like that. But for example, we have been involved in tire wear measurements where the LP Plus was put on board on the back seat actually. So, and there were, for example, no problems in that one. So it is also possible to have a bit harsher conditions to make it work with the proper installation. And okay, there was still one open question in chat. Which particle density was set for this measurement campaign in the LP Plus? I guess this might have been related to the ITT measurements, where the LP Plus CPC comparisons also. I think the particle density was set at 1 in those measurements. But as Erkki mentioned, actually the particle density for the number concentration does not affect, or it doesn't affect the mass concentration that much. It more affects the number concentration, number size distribution. But if you want to have more information on the particle density, as Erkki mentioned, we have a technical note on that and can further discuss it via email also. But we can also just ask us for more information. We'll be happy to send it to you, and might also cover it in some upcoming webinar. So with that, I could wrap it up. And as shown in the last slide, we have a YouTube channel where the webinar recordings and other videos are available. The latest webinar recording is there on filtration research, and also this webinar will be available probably latest by next week. But at the end, I want to thank you all very much for attending. It was very nice to have this webinar with you, and hope to see you in the upcoming webinars as well. So keep looking at them and keep posted. Thank you very much.